Hello everybody. Today we're going to work on Unit 5, gases. You have your printed out fill in the blank notes to go along with us as we go. I will let you know it's about 40 slides. It's a good amount of time. We're going to work out a couple practice problems. Get your calculator handy, maybe a periodic table. I'm hoping to keep this around an hour. This is obviously the first one I've done. Please, at the end, if you have any feedback, what I could do to make it better. Hopefully you can see everything as we go through the video. Kind of how it's going to work. I'm going to have the PowerPoint posted on here like this. So you can fill in the blank notes as we go. And as I go through the PowerPoint, it'd be just like we were doing before, except I'm going to be talking about it kind of in the background to give any feedback I have. Just the blue is what you need to write down. I'm not going to wait for you to finish writing. Feel free to pause the video as necessary to write in the things that you miss. We're going to do some practice problems later. So as we get to the practice problems, I'm going to work them out on paper here. Just work them out on your paper as well. Hopefully it's better to get my direct feedback than to get just reading from the original PowerPoint. So don't want to take too long. I'm going to do my best to get it done as fast as possible. So this would be Unit 5. All right. This section's all about gases. It's our most math, straight up math chapter. There's a couple of concepts we're going to talk about, but it's pretty much just math. We know a lot about gases already. We know that they uniformly fill their container, meaning they're going to spread out evenly over time and diffuse into their entire container. We talked about what the molecular structure of gases look like. The molecules are moving really, really fast and independently. They have almost no intermolecular forces exerting on each other. They mix completely with any other gas. It doesn't really matter what the gases are. They're not going to separate into layers like liquids would because that really low intermolecular forces. And they exert pressure on the surrounding. We're constantly feeling pressure all around us from gas molecules hitting our bodies. Gas molecules are whirling around us all the time, hitting against the buildings, keeping our stuff where it needs to be. You don't want no pressure. That's like what space is like. Your body can fall apart, and we like our bodies together. We're going to talk about pressure. Its scientific definition, it's how much force is exerted over a certain area. We're going to talk about pressure with gases, and that's basically it. You can also have water pressure and stuff with liquids, or gravitational or buoyant pressure, stuff like that. But that's more like physics stuff. We're going to use the SI unit is pascals, which we'll use a little bit, but we're going to learn there's a couple of different units of pressure. At the bottom here of the slide, we have all the different units we're going to deal with. There are more. The main one is this first one, 1 ATM. That stands for atmospheres. That's the one we're going to use most frequently, honestly, because the numbers are the smallest and easiest to use. The 101.3 kPa stands for kilopascals, or 1,000 pascals. That's technically the SI unit. You use it a lot in physics, but we use it very little here. And then the last two have their different applications. Millimeters of mercury is what the first one says, 760, and then 760 torr. And what all these numbers are, this is how you convert between these different 4 units. These are just our unit conversions, which we're going to practice here in a second. It's 1 ATM is 101.3 kilopascals, which is also equal to 760 of those others too. Different tools used to measure pressure, things like barometers. I don't really care about all this. It's fine. Another one, manometer. It's a device used for measuring the pressure of a gas in a container. The only thing you need to know about these, you don't need to know how they work. You just need to know that the words will be used. Manometer and barometer will be brought up in a question, like a manometer or barometer was used to measure the pressure. You could ignore it. Just know that that's what we use to measure pressure. But it's just so if you see that word, don't get confused by it. Okay, over here we have our first example problem. I'm going to work it out as we go here. All right, so pressure conversions. We're going to use these throughout other questions, so it's important to get them down. It says the pressure of a gas is measured as 2.5 ATMs, 2.5 atmospheres. We're going to represent or convert this pressure in both torrs and pascals. So, starting with my 2.5 ATMs, and I want to turn that into torr and I want to turn it into pascals. Okay, and pascals might sound a little bit weird. We talked about kilopascals, kPa. Pascal is just 1. Kilopascal is like 1,000 regular pascals. So we'll deal with that at the end. But we'll have a conversion between them. On the last slide, we said to convert between these, we said 1 ATM is equal to 101.3 kPas, which is equal to 760 torr, which is equal to 760 mmHg, millimeters of mercury. You don't have to memorize these values. They're given to you exactly like this on your AP Chem formula sheet. So as long as you know what the units are, you don't have to memorize the numbers. Now to do a conversion between them, I'm going to start with my 2.5 ATMs, and we're just going to start with torr. I'm going to draw my unit conversion, my train track. ATM's on top, so I'm going to cancel it by putting ATM on the bottom and put the unit I want, torr, on the top. Okay. Now my conversion between these is what I use these numbers on the right for. 1 ATM, so I'm going to put a 1 by ATM, is 760 torr. So I'll put 760 by torr. I'm going to multiply across the top, so my 2.5 times 760, divide by 1, I get 1900 torr. And that's it. So it's just that one-step conversion between ATM and torr. I'm going to do the same thing now for my pascals. So we're going to set it up basically the same way. 2.5 ATM, 1 ATM on bottom to cancel out. This time I'm going to look for pascals, except I don't have regular pascals, I only have these kilopascals, these kPas. So I'm just going to go ahead and convert it to kilopascals. 101.3 kPa. I'm just going to go ahead and solve it with one step, just like we did before. Multiply these across, and I get 253.25. I'll keep a couple of decimals because we're not done yet. Kilopascals. A kilopascal is 1,000 pascals. So if I just times this by, just say 100, I meant 1,000. It's times it by 1,000, and I'll get 253, and I'll just round it to 3 significant figures. So I'll just keep the 3 numbers, make the rest of them zeros. And that's how many regular pascals I would have. Okay. All right. Now we're going to get into a series of a couple of different laws, all named after different scientists. We're going to do an example of each one, but they're pretty easy, they're really fast. And then at the end, we're going to say they all don't matter and combine them all into one law. But just to give a brief example of each one, we're going to start with Boyle's Law, named after Charles Boyle, the scientist who discovered it. I think that's his name, don't fact check it. Basically, he said that pressure and temperature, pressure and volume are inversely related. Meaning as pressure goes up, volume goes down, or vice versa. And he used that to write this first equation I'm going to use here. P1V1 equals P2V2. So the ones, this P1V1, we're going to use that a lot today. That's just talking about our initial gas, or our gas like before something happens to it. And then the P2V2 will be after. Okay. So let's just go ahead and get into an example of it. Spoiled the answer, my bad. So, next, I have my formula we were just talking about, my P1 V1 equals P2 V2. If it wasn't clear, if I didn't make it clear earlier, P is for pressure, V is for volume. Pressure can use any of those units we talked about before. The ATM or the kPas, any of those is fine, but just make sure to stay consistent inside the problem. So if this is P1's an ATM, so should P2. Now, volume will be in liters. When we talk about gases, they take up a certain amount of space. We always use liters as our main unit for that. So usually it's given to you in liters. Sometimes I could be mean and give you like milliliters or decaliters or something. You have to convert it to liters, but that's basically it. So I'm going to look at the problem here. It gives me a lot of information. It says a sample of helium gas, doesn't matter that it's helium, but sample of gas, occupies 12.4 liters at 23 degrees Celsius and 0.956 ATM. So all of that first sentence there is talking about our P1, our V1, right? It's our initial, before something happens to it. So I'm going to choose the left side and put all that over there. My pressure one, it tells me, is that 0.956 956 ATMs. My volume one is 12.4 liters. It gives me the temperature, but I don't need temperature in this one. And if I want to know why, you can read towards the end a little bit. It says temperature stays constant. If the temperature doesn't change, it has no effect on the volume or the pressure. So only pressure and volume. The temperature is just a bit of extra information. So that's my left side, my initial conditions. On the right side, it says what volume will occupy. So that's my V2. That's what I'm looking for. If I have 1.20 ATMs of pressure. 1.20 ATMs. What volume do I occupy? V2. Okay. That's basically it. Now we're just going to solve for our missing variable, V2. So we're just going to multiply the left side together, and I get and then divide by 1.2. When I do the whole thing, I get 9.88 liters. Lost where I did my math. Okay. So I just multiply the left two numbers, divide by 1.2 to get V2 by itself. 9.88 is the answer. And that's all you have to do to solve Boyle's law. All right, next is Charles' law. It's simply the same thing, except we're using two different variables. We're using volume and temperature. He said volume and temperature are directly related, meaning when volume goes up, so does temperature, or when temperature goes up, so does volume. They are directly related. And because of that, we're going to have this new equation, where I do V1 over T1 equals V2 over T2. We set up a proportion. One other key thing we need for this, volume is going to be just like the last problem, hopefully given to you in liters. And then temperature is either going to be given to you in Celsius or Kelvin. Now, you need to make sure you use Kelvin regardless. If the problem gives you Celsius and it wants its answer in Celsius, doesn't matter. Any math you do with gases, that'll apply to this problem or any problem in this entire chapter, always use Kelvin. Don't use Celsius. The reason being, if we look at this equation, right? Let me flip it over here. If I look, I just wrote down the equation. If I use Celsius, it's possible that it's a negative number. You can have a negative degree Celsius. It happens all the time. I could have negative 5 degrees Celsius today, right? But Kelvin is a positive only number scale. So it's impossible to have a number that's 0. Well, that'd be absolute 0. But we can't reach absolute 0. And there's absolutely no negative numbers. If you have a negative temperature, that means when you do some math, you can end up with a negative volume. And you can't have like a negative volume. That doesn't make sense, right? Because of that, so that doesn't happen, we only use Kelvin. Now to get from Celsius to Kelvin, Kelvin is essentially the same, it's just adjusted. Just take whatever degrees Celsius you have, add 273, and you're in Kelvin. Okay? So in this problem here, we're going to need that. Okay. Suppose a balloon containing 1.3 liters of air, that's my volume, at 24.7 degrees Celsius. That's my temperature, but it's in Celsius. So I'm going to have to turn that into Kelvin in the problem. It's placed in a beaker containing liquid nitrogen at negative 78.5 degrees Celsius. Okay, again, it's in Celsius. I'll have to turn that into Kelvin. What will the volume of the sample of air become with constant pressure? So the constant pressure bit makes sense because if I look at this equation for Charles' law, there's no pressure. So it doesn't matter that the pressure, it doesn't affect anything because it doesn't change. I'm going to plug in what it tells me in the problem. My first volume is that 1.3 liters. My first temperature is 24.7, but I'm going to add 24.7 to 273 to get my Kelvin. So add those together and I get 297.7. So that's what I'll plug in here on the left. 297.7 equals. Okay, I have what volume of the sample of air. So V2 is again what I'm solving for. Over T2 is my second temperature, which is negative 78.5 degrees Celsius. If I plug that in, that would give me a negative volume as my answer. But I need to make sure to add my 273 to turn it into Kelvin. And that equals 194.5 Kelvin. So that solves the negative issue for us. Plug in 194.5, and now I'm ready to solve. I have all my variables except for V2. There's a couple different strategies you can use to solve these problems. One way to solve proportions is to cross multiply, and you would set the one cross on the left, one cross on the right. But that's kind of a mathematical way to do it. The easiest way to do it with this type of problem is just to simplify the numbers. 1.3 divided by 297.7. I can just solve that with my calculator. And I get something like that. And it'll simplify the right, but it's pretty much already simplified in this problem. Okay. And now I just solve for V2. I just have to multiply both sides by this 194 to get V2 by itself. And when I do that, I get 0.849 liters for my new volume. Okay. So that one there is Charles' law. The next one's going to be essentially kind of the same idea. We're taking two variables and comparing them. Okay, this one's called the Gay-Lussac's law. This is the proportionality between pressure and temperature. I'm sure all these things when they were discovered were important, and that's why they named them after the people. But knowing the names of these scientists or the names of the laws is completely irrelevant for us. We just need to know these proportionalities. And we have one formula at the end that kind of combines them all to make it way easier. Okay, so just like the last time, this one involves temperature, so we also do need to include our, put it in Kelvin, don't leave it in Celsius. But our equation this time is pressure P1 over T1 equals P2 over T2. So let's look at an example. Okay. A contained gas has a pressure of 564 millimeters of mercury. So we're using that different pressure this time. Okay, 72 degrees Celsius, I'm going to have to fix that by turning it into Kelvin. And then it says at what temperature, so I'm looking for my new temperature, T2, would the pressure of the gas increase to 1.5 atms? Okay, so I'm going to use my left side here. I have two different units of pressure. I have the first one's given to me in millimeters of mercury. Second one is given to me in atms. Doesn't matter which one you choose, but they need to be the same unit. Okay? So what I'm going to do this time, I'm just going to leave the one it gives me here. My 564 millimeters of mercury. I'm going to divide it by my temperature 1, which is 72, but I have to take that 72 and add 273. And I get 345. That's my temperature in Kelvin. That's what I'll put down here. Even if the problem has no negative numbers, you need to convert to Kelvin. Okay? My pressure on top up here is 1.5 atms. I can't just plug that in directly because it's in a different unit. So I'm just going to take my 1.5 atms and quickly convert that into the same one I had on the left side. So atm on bottom to cancel. This on the left is in millimeters of mercury. So I'll put that on top. Going back to the previous slide, 1 atm is equal to 760 millimeters of mercury. Multiply across, and I get 1140 millimeters of mercury. There we go. That's what I'm going to plug into the top over here. It would have been just as good if I would have taken this 564 and divided it by 760 to turn it into atms. If you look on the slide, that's actually what they did when they solved this practice problem on the slide. Either one is fine. Equals T2 on the bottom. When I solve for this T2, it'll be in the same unit as this one. So when I get this answer, it'll be in Kelvin, and I'll be done. Okay, so I'm going to go ahead and simplify. I'm going to divide the left side. 564 divided by 345. 1.6348 equals my 1140 over T2. Okay, now I'm just going to solve for T2. I can't really solve that on the bottom here, so I'm just going to multiply it up. Multiply both sides by T2, or you can think about just moving T2 up here. Okay, and then just dividing by 1.648 to get T2 by itself. I get 697.3. I'm just going to leave it as 697 to keep it in 3 significant figures. So usually, if you're worried about rounding, just round it to 3 non-zero numbers. If I want the unit, it is in Kelvin. And that's that. Regardless of what unit you converted your pressure into, you'll get the same answer. Right. Avogadro's law. The last of these 4 laws. This is our last proportionality. This is volume and moles. Okay. The volume of a gas is proportional to the amount of moles. I know moles are confusing, but just think about moles as how much gas you have. So the more moles you have of a gas, the bigger the volume it occupies. It makes sense. The less moles of gas you have, the volume it occupies goes down. So it makes sense that they're proportional. All right. I'm going to write down the equation because we're going to do a practice problem. Of course. All right. I have 2.45 moles of argon gas occupying a volume of 89 liters. What volume will 2.10 moles of argon occupy under the same conditions of temperature and pressure? So this was an example of when I'd use Avogadro's law. I have 2.5 more moles of argon and I know how much space that takes up, but I'm going to reduce the amount of argon to only 2.1 moles, and so I'd expect it to take up a little bit less space. I'm looking at this, I'm expecting my answer to be maybe like 75 or something. If 2.45 moles takes up 89 liters, then 2.1 is a little bit less, maybe it'd be like 75 liters or something. But we can solve it exactly just using this formula. Volume 1 on top, so I'm going to use 89. Moles 1 on the bottom, 2.45. Real quick about the 1s and 2s, it doesn't matter which side you put your 1s or 2s. They're equal to each other. So no matter if you put the initial information on the right or the left, it doesn't matter. What really matters is that you pair up the right information. So this 89 liters is applying to this 2.45 moles. I could have put it here on the left, I could put it on the right, and I would get the same answer. But just know to keep them paired up together. So the next part of the question says, what volume, so that's a V2, that's what I'm looking for, will 2.1 moles of argon occupy under the same conditions? So I have all my variables except V2, I'm just going to solve. So I'm going to divide this out, multiply by 2.1, and get my final answer, 76.3 liters, which is a little bit less than the 89 that we guessed. So yeah, 76, that answer makes sense. All right, well, we learned about those 4 separate laws, but like I said, you don't really need to know them. You just need to know the combined gas law. But it's not given to you necessarily on the formula sheet in this context. I think part of the other laws are, but like not this one. So I would definitely commit this to memory. And we're going to practice it a good bit, so this one's really important. So I have P1 V1 divided by T1 equals P2 V2 divided by T2. So that's my left side. My pressure, volume, and temperature of my gas to start with is equal to the ratio of my pressure, volume, and temperature when I end. This kind of combines all the different laws except for the one with the moles. You'll notice there's no moles in here. That's fine. But it combines all the other ones. And what I would recommend doing, instead of memorizing all those different other ones, is just always use this one. If the problem tells you that one of them is constant, like this problem, a problem tells you that temperature doesn't change, then just get rid of temperature. Just cross off the temperature in the problem and only do pressure and volume. And that's just another way to get Boyle's law, whichever one that is. If the problem tells you pressure doesn't change, then just cross off pressure. Right? So I would just recommend using this one, and if anything constant, you can just get rid of it on both sides because it doesn't change. Okay. Let's do this example. So I have my formula here, my combined gas law, pressure 1, volume 1 equals over temperature 1. I'm just going to plug in what I know. It says at what temperature in Celsius, that's a bit annoying because we're going to have to do Kelvin inside our problem, so we'll have to turn it into Celsius at the end, but that's okay. Does 121 milliliters, also a little bit annoying, but I just know 121 milliliters a milliliter is there are 1,000 milliliters in 1 liter. So if I just divide that by 1,000, that turns it into liters. So that's just 0.121 liters. Of carbon dioxide at 27 degrees Celsius, this is a super annoying problem. 27 degrees Celsius, I have to turn that into Kelvin. Plus 273, and that equals 300 Kelvin. Okay. And 1.05 ATM. Okay. So it says at what temperature does 121 milliliters of carbon dioxide at 27 C and 105? So all of those variables, my carbon dioxide, my 121 milliliters, 27 C, 1.05 ATM, that's all one side. So I'm just going to choose the left side for that. My initial pressure, 1.05. My initial volume is my 0.121 we converted into liters. And then my initial temperature over here is the 27 Celsius, which we made 300 Kelvin. Okay. Occupy at a volume of, so I'm going to change my volume to 293 milliliters, which I'm just going to do 0.293. At a pressure, my new pressure is 1.4. So I'm going to plug in my new information, 1.4. My new volume is my 0.293. Divide by my temperature is what I'm looking for. What temperature does this occur at now? Okay, it doesn't matter which side's which, but you should have all the group information paired together. And now we're just going to combine everything, simplify to solve for T2. This left side, I'm going to multiply the top and then divide by 300. And that just simplifies to not a whole number, to a decimal, like that. And on the right side, I'm going to multiply the top to simplify my numbers. And I get 0.4102 divided by T2. And now it looks less intimidating. There's annoying numbers, but I'm just going to multiply T2 up like we did before. Times T2 equals my 0.4102. And then just divide each side by this long number to get T2 equals 969 Kelvin. When I get this answer, I know it's in Kelvin because I input Kelvin over here. Okay. But the question did ask for it in Celsius. So to turn this into Celsius, I'm just going to subtract 273 from it. And math, sorry, I can't see, is 696. Is that right? Okay. It's weird how those numbers line up. Okay. Cool. Here's where I would say any questions, but I'm talking to a screen. All right. Let's go to the next thing. All right. The last big law we need, the last big formula, is the ideal gas law, which hopefully is familiar to you. This is dealing with what we call an ideal gas. An ideal gas is a simplification of what a real gas would look like, but it's like a perfect gas. It's going to make our math way simpler. What an ideal gas needs to have, which we're going to talk about a bit more as we go, it basically takes up no space at all. We pretend like the individual gas molecules take up a volume of exactly 0, and we pretend that they have no interactions with any other molecules or with the container that they're in, which isn't entirely true, but it makes our math simpler. So we're going to talk about the non-ideal gas formulas later in this chapter, and you'll see how terrifying they are. So here we have our PV equals nRT, PivNert. This one is on your formula sheet. This one will be used often. It's probably the most likely question to come up is solving the ideal gas law. We're going to do a couple examples today, but plenty more examples in class. So I have P is pressure, V is volume, N is back its number of moles again, and then we have a new one, R. R is called the gas constant, and we're going to talk about it, but there's actually 3 different numbers. They're constants, but it depends on which volume you use for pressure. This example here has pressure in ATM and atmospheres, which is the most typical. With pressures in atmosphere, then the R you use is that number there, the 0.08206. So just ignore those units because they're terrifying as well. And then T is temperature. It'll be in Kelvin for this as well. This one only has one set of pressure, volume, temperature. You're not doing a before and after sort of change like we were with the combined gas law. This one you are doing just like one set. If you have some of the information about a gas, you can figure out the missing temperature or volume or number of moles. Okay. So we'll start with an example using the ideal gas law. Don't know if I've made this clear. Just to clarify, on like this slide, it has the answer worked out in blue. You don't need to write that if you just write down the examples I do. Like I don't want you to have to like double your work. Okay. PV equals nRT is my ideal gas law. You definitely need to use this equation a lot. I have an automobile tire at 23 degrees Celsius. That's annoying. Let me take my degrees Celsius, add 273, and I get 296 Kelvin. Okay. With an internal volume of 25 liters, great. Liters is good. It's filled with air to a total pressure of 3.18 atmospheres. So that's my pressure. Determine the number of moles of air in the tire. Okay. So pressure, it said, is 3.18. Volume is that 25 liters equals N, number of moles, times R. So I'm going to write out the gas constants. They will be given to you on the formula sheet as well, and we'll definitely talk about them in class. It depends on what unit you use for pressure, what R is going to be equal to. When you use atmospheres, which is the most common, R is going to be 0.082. It says 06 in these notes, or you can abbreviate it to just 0.0821. By rounding, it's like one less decimal place. So this is the number I usually use, but I do think this longer number is given to you on the formula sheet. But either one you use, you'll get basically the same answer. It's totally okay to use either. If for pressure you use kilopascals, kPa, then R is going to be 8.31. Sometimes you'll see it written as 8.314 or something like that. But I use 8.31. And then for the other two, for torr or millimeters of mercury, they're equal to each other, so they share the same R constant. It's 6236. So R just depends on which pressure you have in your problem. So like this one, it gave us ATM, so I'm going to put in this number, 0.0821. And I'm going to put my temperature, make sure to put the Kelvin temperature of 296. All right, now I have all my variables except one, so now I just solve. I just multiply the left part together, then multiply the right part together, and that's it. 79.5 equals 24.3016 times n. Solve for n by just dividing it by itself. And I get 3.27 moles. So that's how many moles of air I have. And there's the whole problem. Hopefully that's not too bad. Okay, we're going to do another problem using the same law. All right, so I'm going to write the ideal gas law again. Pivnert. What's the pressure? So that's what I'm looking for. P. Of a 304 liter tank. Okay, that's my volume. That contains 5.67 kilograms of helium. There's no mass or grams anywhere in here, so we can't use that directly. But if I have grams or kilograms, I can turn that into moles by doing some unit conversions. So let's go ahead and do that. I have my 5.670 kilograms of helium. Well, a kilogram is 1,000 grams. So if I just times that by 1,000, I get 5670 grams of helium. Okay, I can turn that into moles by using a unit conversion. To convert from grams to moles, we use, of course, the periodic table. I'm going to find helium on the table, which is in the upper right corner here. It weighs 4.003. We're just going to round it to 4. Weighs 4 grams for every 1 mole. So that means 4 grams of helium on the bottom, so that the grams of helium cancel, equals 1 mole of helium. 5670 times 1, divide by 4. I get 1417.5 moles of helium. So that's a lot of helium. Okay? But that's my n that we solved for. So I'm going to go ahead and plug in 1417.5. for N. R is going to be my gas constant. Pressure wasn't given to me in a specific unit, so I can choose any unit of pressure I want. Usually, if you have a choice, you would choose ATMs. I'm going to put in the same gas constant from over here, 0.0821, and my answer will be in ATMs because of that. If I chose one of these other gas constants, then the unit of pressure for my final answer would just match with that unit of pressure. Last thing I have here is temperature. I have 25 degrees Celsius, so I have to turn that into Kelvin by adding 273, that equals 298. Okay, so those are all my units plugged in. Now I just solve for my missing variable P. Multiply all the numbers on the right together, divide by 304, and I get 114 ATMs. And that's it. So we added a little twist to the problem by adding in kilograms instead of moles, but we know how to turn that into grams and then into moles, so we can just plug it back into the ideal gas law. All right, back to here. All right, this is basically working out the same problem here. The key thing you need is what you need to write down on the slide. It's STP. Okay, STP stands for standard temperature and pressure. A lot of times to save writing and to make constants equal to each other kind of across the board, we take recordings at STP. And that's just a shortcut to tell you 0 degrees Celsius, although we don't use Celsius, we use Kelvin, so it'd be 273 Kelvin, and 1 atmosphere of pressure, or you can use 760 torr, 760 millimeters of mercury, or 101.3 kPas. That's standard pressure. 1 mole of gas, by definition, at STP, has a volume of 22.4. And if you plugged all those values into the ideal gas law, that's what we should get. Plug in pressure is 1, volume is what you're going to solve for. 1 mole of gas, with the gas constant and with temperature being standard, equals 22.4 liters. Okay. A sample of oxygen gas has a volume of 2.5 liters at STP. How many grams of oxygen are present? Okay. More gas law. The problem says nothing about oxygen being ideal, and oxygen is not an ideal gas, but unless it says otherwise, just always use the ideal gas law formula. We're just implied that it's going to be ideal. Okay. So pressure and volume, well, it's at STP, so pressure is standard, it's just 1 ATM. Volume, it tells us, is 2.5. Number of moles of gas is unknown, so we're going to put N. The problem is looking for grams, so similar to the last problem, if I can solve for moles of gas, I can turn that into grams. R is my gas constant. I chose ATM as my pressure, so 0.0821 is my gas constant. My temperature is standard as well. It's 0 degrees Celsius, which is 273 Kelvin. Okay, I'm going to multiply the left, multiply the right, divide everything over. I have 2.5 on the left, 22.41 times N on the right. Divide both sides by 22.41. I get 0.1116 moles is N, but the problem wants grams of oxygen. I have moles of oxygen here, so I'm just going to do a little unit conversion. Okay, moles of oxygen on top, so I'm going to put moles of oxygen on the bottom and convert it into grams of oxygen. So I need to go to my periodic table, find the molar mass of O2. Oxygen here is 15.999, let's just round it to 16, and then times by 2 because there's 2 of them. So an O2 molecule weighs 32 grams per every mole. So 32 grams in 1 mole of it. Multiply across. 3.57 grams of O2 is my final answer. All right. On to the next topic. That's it for ideal gas law for now. Is Dalton's law of partial pressures. It says for a mixture of gases in a container, your total pressure is just equal to the individual pressures of all your other gases. Basically, I have 3 different gases in one container. Just add up the pressure of all 3 of them. They are additive, and the total pressure is just the sum of all of them. Okay. There's some fancy math they're doing here on this slide, rearranging everything. But essentially what you need is that top formula. Just know the total pressure of a gas is just equal to the additive, to the sum of all the different gases in the container. Okay, so here's an example. 3 ideal gases, A, B, and C, are mixed and added into a previously evacuated container. So previously evacuated just means it was empty beforehand. You'll get a lot of science lingo like that and problems like these. Previously evacuated rigid container just means a container with no holes in it that works perfectly and is a vacuum beforehand. But basically, you just ignore it. Basically, just means you don't have to consider the container in the problem. The total pressure of the container rises to 14.2 atmospheres with all 3 gases in it. If 2300 torr of A and 2800 torr of B were added, what pressure of C was added? Okay, so basically here I have my total pressure, which I'll write PT, is equal to all 3 of my pressures. Pressure A plus pressure B plus pressure C. It gives me pressure A, pressure B, and it gives me the total pressure, and we're just solving backwards to find what pressure C had. Only issue I see is that they're in different units. So my total pressure is 14.2 ATMs. That's my total pressure. But my other pressures, A and B, are given to you in torr. So we have to have the same unit for everything to add it all together. So I'm going to start with this 14.2 ATMs. I'm going to choose to turn that into torr. I could also take the torr for A and B and turn those back into ATM, but that seems like more work, so I'm going to do it this way. 14.2 ATM, 1 ATM on bottom equals 760 torr. Multiply across, get a big number. I'm going to leave the full number like this until I'm done with the problem. I'm not going to round yet. I have 10,792 torr. That's what I'm going to plug into PT. My pressure A and B are given to me in my problem, and now they're in the right unit. So I'm just going to add 2,300 torr plus 2,800 torr plus pressure of C. And now we have a pretty easy equation to solve. I'm adding everything together here, so just subtract 2,300, then subtract 2,800, and you'll be left with just your pressure of C. And I get my 5692, or you can round it 5690 if you want to keep your 3 sig figs. So technically, that might be the more correct answer. Okay. Next, we have mole fractions, which we actually talked about last chapter, right? Basically, the same idea is going to stay here. A mole fraction is mole of one gas is what we're going to use here. How many moles of one gas divided by your total number of moles of gas. And we're going to use mole fractions for a couple of different problems. At the bottom, what they're doing here, substituting in the ideal gas law, you could factor out this other equation. We're not going to use that one, though. Basically, what it's saying is, I'm really looking over here at the right, over here at this P1 equals X1 times P total. If I want to know the pressure of one gas, pressure of gas 1, that's equal to the mole fraction of that gas, say 0.25, times the total pressure. So if I want to know the partial pressure of just one gas, all I have to do is know the mole fraction of it and just multiply by the total pressure. Let's do an example. "40 grams of argon gas." Okay. We haven't talked a lot about what this little symbol means, this G here. Just know that that G means gas. We're going to talk about all the other ones as we do chemical reactions after the break. Okay, it's added to 16 grams of helium in an airtight container that was previously empty. What's the mole fraction of argon in that container? Let's start with that. So I gave you 2 gases, but I gave them to you in grams. We usually don't do anything with grams. We're just going to convert those into moles. Okay? So what I'm going to do is I'm going to take my 40 grams of argon, turn that into moles. Grams of argon on the bottom, moles of argon on top. To switch it, I need to go back to my periodic table. Argon is right here. Let me scroll down a touch. There we go. Argon weighs 39.9. We're just going to round it to 40. 40 grams per 1 mole. Now I'm going to solve, multiply the top, divide by the bottom. I just have 1 mole of argon. Now I'm going to repeat that for helium. I have 16 grams of helium. I'm going to convert it, go back to my periodic table. Helium up here at the top is 4.003, just round it to 4. There are 4 grams of helium in every 1 mole of it. So if I solve, 16 times 1, divide by 4, equals 4 moles of helium. All right. The question asks, what's the mole fraction of argon? So I have my mole fraction, the capital Chi, the weird X thing. It's just my moles of argon divided by my total moles. My moles of argon is just 1. Divided by my total moles, well, I have 1 mole of argon, 4 moles of helium, so I have 5 total moles. 1 divided by 5, 0.2. My mole fraction of argon in this problem is just 0.2. Remember, this one you don't times by 100. It's not mole percentage, it's mole fraction. So leave your answer as a proportion. All right, the second part of the problem says, what is the volume of the container at STP, assuming the gases are ideal? So, I have the ideal gas law. That's what we're going to need. It's at STP, which tells me the pressure and the temperature. The R is a constant, I know that. So all I have here is the volume is what I'm looking for, and N, which is the number of moles. Well, remember, when you have multiple moles of gas, you just add them together to get the total number of moles. So I have my 1 mole of argon, my 4 moles of helium, and like we did over here, I just have my total number of moles equals 5. It's just the number of moles of argon plus the number of moles of helium. So I'm going to plug 5 into the ideal gas law. The pressure is 1. The volume is what I'm looking for. My moles is 5. R, I'm going to use the constant for ATMs because that's what I use there. Temperature at STP is 0, so I'm going to make it 273 Kelvin. Multiply just the right side together to solve for volume. Volume is 112 liters. Okay. All right. That's the bulk of the math. And now we just have a couple concepts to talk about, and then we'll be nearly done. All right. A couple of these postulates of the kinetic molecular theory. A lot of problems about this in this chapter that are kind of conceptual. We'll talk about more in class. But I just want to start kind of with the their tenets or postulates. Number 1, the particles are so small compared with the distances between them that the volume of individual particles can be assumed to be 0. Basically, it sounds like the ideal gas law. Kinetic molecular theory is just a theory about how gas molecules move. So our first assumption we're kind of making here is that gas molecules are really, really, really tiny, which they are, and don't really bother each other. Particles of a gas are constantly in motion. The collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. So this is saying all the molecules don't stop moving, which is pretty much true. They're constantly moving in different directions. Remember, if those molecules slow down, they're going to revert back into a liquid and then eventually into a solid. The reason that they're a gas is because of the motion that they have. Particles are assumed to exert no forces on each other. The particles interact independently. They bump into each other, but when they bump, we assume it's a perfectly elastic collision, so no energy is lost. They bump into the side of the containers, and it's fine. They're assumed neither to attract nor repel each other. No intermolecular forces between them. And then this last one has to do with the energy of a gas. The average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. Temperature of a gas increases, the average kinetic energy of the particles does too. And we have this equation to kind of solve what is the kinetic energy of a sample of gas. The kinetic energy of gas particles will be calculated by kinetic energy, Ke, equals 3/2 times RT. R is going to be the gas constant, but it's going to be the one that's the SI unit technically, which is kilopascals. So it's the 8.314 number, and T is temperature in Kelvin. Now, this equation is not something we solve. It's kind of a conceptual equation, kind of like Coulomb's law. Basically, what you need to understand is as the temperature of the gas increases, so does the energy of the gas. So if you're comparing multiple samples to each other, the one that at a higher temperature will have a higher average kinetic energy. Another intimidating looking formula that really is essentially the same idea. And this weird variable on the left, this URMS, that stands for root mean square velocity. We've talked about this idea a little bit, but molecules in a gas or a liquid or whatever, they don't all move at exactly the same speed. There is a distribution of speed. Some are moving a little bit faster and slower. There's like an average speed where most of the molecules move, but some move faster or slower. So if we want to talk about the velocity of the molecules, we have to use like an average. The root mean square is that average. We take this, we square the average velocity, and then take the square root, which is a really fancy way to take the absolute value of something. So basically, this is just the average speed of a particle. But we have to write this weird variable to be more technical. It's equal to the square root, which we don't use very often, times 3RT over over m. 3 and r are just numbers. R is that same 8.314. 3 is just a 3. The square root's a little bit weird, but we really can just ignore it. T is on top. T stands for temperature. Okay, so the higher the temperature is, because it's on the top of the fraction, the higher the root mean square velocity. And then divide by capital M, which stands for usually molar mass of whatever gas molecule you're looking at, or the mass of a mole of gas, usually written in kilograms. But the M is just how big is the gas. Okay? You notice that's on the denominator. The larger the gas is, the slower the particles move on average. Think about it like applying the same energy to a bowling ball or a baseball. If I punch each one, the baseball, I'm going to punch that one a lot further than I can punch the bowling ball. The larger a particle is, the slower it moves. And that's kind of what you need this formula for as well. There'll be multiple choice problems, and some we'll do in class, where I'm giving you multiple different molecules to compare them. Maybe helium and argon and neon. And you have to say which one has the highest root mean square velocity at constant temperature. The smaller something is, the faster it's going to be. The faster its root mean square velocity will be. The larger something is, the slower it's going to move. That's essentially what this formula is for. We've got a little bit of vocab to talk about. We have effusion versus diffusion. Diffusion is talking about just the mixing of gases. If I spray like some Febreze over here by me, it's going to spread out into the entire room by random chance because all the molecules are moving in random directions. So if I give it enough time, by random chance, they'll be pretty equally spread throughout the room. It's kind of the concept of entropy, which we'll talk a little bit more about later in the year. And then there's effusion with an E. That describes the passing of gases through like a tiny hole or orifice or seeking through other means like that into an evacuated chamber. So like if you had a balloon, over time, over a couple of days, the balloon starts to deflate a little bit because the gas molecules are able to escape the balloon. They're able to leak out of it through tiny little holes in the nylon or whatever type of balloon you're using. The gas is eventually able to escape. And that's why the balloon gets smaller and smaller over time. The main idea we have here is the rate of effusion depends on the type of gas. Really small gases like helium escape really fast. They have a high rate of effusion because they're so tiny. They can kind of fit through those little cracks. And they're moving faster, so they have more chances to hit the side of the container, the balloon, whatever it is, and escape. So the rate of effusion of small things is much higher than larger things. Larger things have more trouble fitting through the gaps of the material, and they are moving slower, so they hit the sides of the container less often and have less chances to escape. So a balloon full of xenon will leak a lot slower than a balloon full of helium. All right. We can actually calculate the rates of effusion for a couple of different gases. So let's try to do that. We have this formula here. The rate of effusion for gas 1 divided by the rate of effusion for gas 2, we have like a proportion set up, equals the square root of M2 over the square root of M1. Okay? M1 and M2 are the molar masses of the gases. Alright, so this is a little bit weird, but let's just kind of look at an example. Alright. Let's say I have one gas whose rate of effusion is 10 meters per second. And the second one, let's say it's twice, 20 meters per second. We can kind of compare them. We can find information about how big they are based off of that. That equals the square root of molecule 2, mass 2. Let's say we know that it weighs 16. So I'll take the square root of that. Over the square root of M1. Okay. If we have this information, we can solve for the molar mass of the first gas when we're comparing them. Okay. So I'm just going to kind of solve this. This is 0.5 equals square root of 16 is 4 over square root of M1. Multiply up 0.5 times square root of M1 equals 4. Okay. Divide. Square root of M1 equals 8. And then we have to take the square of each side. M1 equals 64. Okay, what that means is the mass of my first gas is 64, usually grams per mole. And my first one is only 16. So this one is 4 times bigger. And because of that, it leaks out half the speed. Right? It's going to leak out at half the rate of the first one. Right? Because it has this weird square proportionality. So if you double the rate of effusion, you're quadrupling the size. Essentially is what's going on there. Alright. Nearing the hour mark, but we are just about done. Alright, now comparing ideal gases to real gases is kind of the last thing we're going to do here. We're not going to solve any of the equations with this, because, spoiler, the equation looks like this, and that's gross. Okay, but we do need to understand why something's ideal and compare which gases are more ideal than other gases. An ideal gas, if you remember, has absolutely 0 intermolecular forces and takes up 0 volume. Okay. So if the pressure of the gas is high or the temperature is low, the gas isn't going to be very ideal. Because under these conditions, the concentration of the gas particles is high and attractive forces become important. The slower the molecules are moving, the more they're going to attract each other. So it's going to mess up our math. Okay, here's a couple examples of different molecules, how their pressure interacts with their, or how their ratio of pressure volume interacts with the other variables, depending on what the pressure is. A straight line would be a perfectly ideal gas, which you see you don't really have. None of these gases are perfectly ideal. Some of them, the ratio here changes at different pressures. To correct the pressure, you can put in this disgusting correction. For real gases, the actual observed pressure is lower than the expected pressure due to the intermolecular attractions that happen. Basically, the gases stick together a little bit more, hitting the sides of the container less often than they would have, because they're getting kind of like pulled around each other, kind of attracted to each other. Here are the values of this constant. This is gross. I don't even care if you write this part. Here's the corrected volume. This is the second part of being an ideal gas, is having no volume. So this minus NB part takes out the volume of your individual molecule. What you should know, though, is for a real gas, the volume available to a gas particle is lower. Okay, think about if you have a 1 liter size container and you fill it with a bunch of gas. Well, the container itself is 1 liter, yes, but the collective gas molecules take up some amount of space by themselves. If they were ideal, they would actually take up 0 space, and they would have 1 liter worth of volume. But because they do take up some amount of space, especially when you add a bunch of them together, if you have a lot of gases compressed into a small space, it takes up some of the volume. So that's going to affect your value for the ideal gas law a little bit. Here's the constant of B for some different things. You don't need to know any of these or do any work with these, really. Okay. Here's another one of these charts. Whatever. Okay. As expected, real gas behavior can tell us about the relative importance of intermolecular attractions among gas molecules. Basically, if you want the more ideal gas, is going to be the one that is the smallest, and it's going to be the one that's has the least intermolecular forces with other gases. Small noble gases, like if we go back to the periodic table, like helium, is the smallest element, and it is a noble gas. So it interacts with very little other things, and it's really, really small. Because of that, helium is the most ideal gas on the periodic table. It takes up the smallest amount of space, so the volume part is only a little bit off, and it doesn't really have very many intermolecular forces. Just London dispersion forces, but because it's so tiny, it only has a couple. Things like neon is also a decent ideal gas. It, again, is pretty small, so it doesn't take up very much space, but it has more London dispersion forces than helium does because it's slightly bigger, and slightly bigger, and slightly bigger. All right. Okay, that's basically it for this unit. We kept it around an hour, which is good. Finish your Unit 5 notes, bring them in. We'll talk about this a little bit more because this is the first one. If you have any feedback for me, feel free to talk to me in class or shoot me an email about it. Hopefully this made sense. Hopefully you're able to grab everything. If you have any questions, let me know. Okay? All right. Bye-bye.